Now what is conductivity? Conductivity is the ability of a substance to conduct electric current. And this conductivity of a solution K is equal to, we have studied, it is 1 by R into L by A. And this conductivity of a solution is directly proportional to the number of ions present in the solution. Now, this is variation of conductivity with dilution. What do you mean by dilution? Dilution means the solution is going on diluted. That means we are adding more and more water. So if you are diluting a solution, the number of ions per unit volume will decrease. When the ions per unit volume decreases, the conductivity also will decrease. So conductivity decreases with the dilution. Now next is molar conductivity. Now what is conductance? Conductance G is equal to 1 by R. It is equal to K into A by L. The conductance G is equal to 1 by R, that is equal to K, conductivity into A by L. Now this, suppose we are taking a solution which contains 1 mole of a substance, 1 mole of the electrolyte is taken, and when the conductance measured is molar conductance, then the molar conductance is equal to K into molar conductance. If we are taking 1 mole of the substance in the solution, we have 1 mole of electrolyte. So molar conductance is equal to K into A by L. Now let L, this length of the solution, is equal to unity. That is, we are taking the distance between the 2 electrodes, a unity, either 1 centimeter or 1 meter. Then we can say it is equal to K into A. Now what is volume? Volume is equal to area into length. Isn't it? Volume is area into length. If length is 1, then volume is equal to area. So we can say the molar conductance is equal to K into V. Lambda m is equal to K into V. That is conductivity into volume of the solution. Now as we said on dilution, the conductivity K will decrease because number of ions per unit volume will decrease. But the volume will increase because we are going on adding water. That means volume will increase. The conductivity K decreases and volume increases. So that decrease in conductivity is more than compensated by the increase in volume. That means increase in volume is very high, decrease in conductivity is less. So lambda m will, in effect, what happens to molar conductivity? It increases with the dilution. Molar conductivity increases with the dilution. So this is the change of molar conductivity and conductivity with the dilution. Now the variation of molar conductivity with the dilution is, for a strong electrolyte, is given by the equation lambda m at any concentration is equal to lambda m naught minus A root C. This is called the Debye-Heckel-Onsager equation. Lambda m at any concentration is equal to lambda m minus A root C. What is lambda m naught? It is the limiting molar conductivity. That is, when the concentration reaches to 0, when concentration term it reaches to 0, then lambda m at any concentration will become lambda m naught. So when concentration reaches to 0, that means that much too low if it is, then the measured molar conductance is called the limiting molar conductance. Now this is for a strong electrolyte. Now this we can rewrite as lambda at any concentration is equal to A root C minus A root C plus lambda m naught. This is in the form y is equal to mx plus c, which is the equation for a straight line graph. In the place of y we have lambda m naught, lambda m at any concentration. In the place of x we have root c. So if you plot a graph with at the y axis we have lambda m molar conductivity, and then x-axis we have root c. Then we will get a straight line graph with the slope is equal to, what is the value of slope here? Slope is m. In the place of m we have minus a. Slope will be equal to minus a, and the intercept on the y-axis, that will be the lambda m naught. Yeah, and the c, the intercept on the y-axis will give you the value of c. C here it is lambda m naught. So limiting molar conductivity you can calculate graphically like this. So you find out, this is only for a strong electrolyte. So for a strong electrolyte, you find the molar conductivity of a strong electrolyte at different concentration, plot the graph, then extrapolate to make the y-axis, the intercept on the y-axis will give you the limiting molar conductivity lambda m naught, and the slope will give you minus a, the d base constant. So this is for a strong electrolyte. And what are strong electrolytes? Electrolytes which completely dissociate in solution, aqueous solution, are called a strong electrolyte. Which are the different classes of compounds which come under strong electrolytes? Strong acids, strong bases, salt of strong acid, strong base, salt of strong acid, weak base, salt of strong base, weak acid. All these come under the strong electrolytes. That is strong acids, strong bases, salt of strong acid, strong base, salt of strong acid, strong base, then salt of strong acid, weak base, then salt of strong base, weak acid. All of them come under strong electrolytes. So for strong electrolytes you will get a graph like this, a straight line graph with the slope is equal to minus a, and intercept on the y-axis is lambda m naught. So this is for a strong electrolyte, and this equation is only for strong electrolytes. Lambda m at any concentration is equal to lambda m minus a root c, that I have rewritten it as lambda m at any concentration is equal to minus a root c plus lambda m naught, and this is in the form y is equal to mx plus c. In the place of y we have lambda m at any concentration, and the place of x we have root c. So lambda m is plotted against root c, you will get a graph like this, and if you extrapolate it to make the y-axis, you will get the limiting molar conductivity. So we can calculate the limiting molar conductivity of strong acids graphically. Now, in the place of strong acid, if you are using a weak acid, if you are taking a weak acid and a different concentration, if you calculate molar conductivity and plot it, you will get a graph like this. A graph like this will be obtained. That means, see, there is a steep increase in the curve. This is weak electrolyte, like ethanoic acid, weak, and this is for strong electrolyte. So weak electrolytes will get a graph like this. We cannot, it will not meet the y-axis anywhere. That means we cannot find out the limiting molar conductivity of a weak electrolyte graphically. Now, why the difference here? Here for strong electrolytes you are getting a curve like, a graph like this, and for a weak electrolyte there is a steep increase in the molar conductivity on dilution. Why there is this change? Or why the difference? What is the difference between the weak and strong electrolytes? So for weak electrolyte, when the solution is concentrated, then the dissociation is very less. So dissociation is less, number of ions will be less. When you go on diluting it in presence of polar water molecules, more and more molecules will dissociate and number of ions will increase, which will contribute to the increase in molar conductivity. Now what about then strong electrolytes? Why for strong electrolytes there is a slow increase? Strong electrolytes, even at the highest concentration, it will be completely dissociated. For strong electrolytes, when you go on adding water, what happens? The ions will move apart and the interanic force of attraction will decrease. When interanic force of attraction decreases, the ions are able to move fast. Therefore, conductivity is increasing. But here, for weak electrolyte, that is when you go on diluting it, number of ions goes on increasing because dissociation goes on increasing. When number of ion is increasing, the number of conductivity increases, and therefore the molar conductivity will increase for weak electrolyte. So this is for strong and weak electrolyte. Now the question is, strong electrolytes we can calculate the molar conductivity, the limiting molar conductivity at infinite dilution by plotting the graph and extrapolating it. What about for weak electrolytes? How will you calculate the limiting molar conductivity of a weak electrolyte? For that we can use Coloratius law. Coloratius law. What is Coloratius law? Now according to this law, for any electrolyte, the ions formed by the dissociation, they contribute towards the limiting molar conductivity of the electrolyte. Each ion will contribute. So the limiting molar conductivity of an electrolyte can be represented as the sum of the limiting molar conductivity of the cation and anion, irrespective of the other ion with which it is in contact. Whatever may be the other ion with which each ion is in contact, each ion will contribute towards the limiting molar conductivity. For example, for limiting molar conductivity of NaCl, sodium chloride, is equal to limiting molar conductivity of sodium chloride is equal to limiting molar conductivity of Na plus limiting molar conductivity of Cl minus. Limiting molar conductivity, so Na plus will contribute towards the limiting molar conductivity of NaCl, and Cl minus also will contribute. So the total molar conductivity, limiting molar conductivity, can be written as the sum of the molar conductivities of the contributing ions. For example, another example is barium chloride. Barium chloride, when it dissociates, it will give you Ba2 plus 2Cl minus. That means barium ion will contribute and 2 chloride ions. Each of the chloride ions will contribute. So we can write lambda m of barium chloride as BaCl2. The limiting molar conductivity of barium chloride is equal to the limiting molar conductivity of Ba2 plus each chloride ion will contribute. So both the chloride ions are contributing, so you can write 2 into lambda m naught of Cl minus. Now what is this is take the molar conductivity of the compound, that is any compound, you will write the capital lambda, and for the each ion, cation and anion, you use small lambda. So this is Coloratius law. You can write the limiting molar conductivity of an electrolyte as the sum of the molar conductivities of the contributing ions, that is the cation and anion. So in general, we can write lambda m naught of any electrolyte AB is equal to nu plus lambda m naught of A plus nu minus lambda m naught of B minus. So we don't know how much A plus and B minus will be formed. Let nu plus is the number of cations and nu minus is the number of anions. Lambda m naught of AB is equal to nu plus lambda m naught of A plus nu plus lambda m naught of nu minus lambda m naught of B minus. This is how we represent Coloratius law. Now what are the uses or applications of this Coloratius law? First one, as we said, we can use this to find out the limiting molar conductivities of weak electrolytes. For example, suppose you want to calculate the molar conductivity of CH3COH, that is ethanoic acid. You want to calculate the molar conductivity of ethanoic acid. This is a weak electrolyte. And what is lambda m naught of ethanoic acid is CH3COOH is equal to lambda m naught of CH3COO minus plus lambda m naught of H plus. This is how we will have to find out. That means we must know the lambda m naught of ethanoate ion or acetate ion and that of H plus ion. Now what we can do is we can find out some strong electrolytes which will give this ethanoate ion or acetate ion and hydrogen ion. A strong electrolyte which contribute this ion. What is that ion? You can take sodium acetate. That's lambda ion not of CH3 COONA, sodium ethanoate. Sodium ethanoate. This is a strong electrolyte because it is a salt of weak acid and strong base. Sodium hydroxide and ethanoic acid. So the salt of a strong base and weak acid is a strong electrolyte. So lambda ion not of CH3CON you can find out graphically. So that is equal to lambda ion not of CH3COO minus plus lambda ion not of Na plus. Right? Now, what is lambda ion not? Now we have to find out lambda ion not of H plus. You find an electrolyte which gives H plus ion. Lambda ion not of HCl. HCl is equal to lambda ion not of H plus lambda ion not of Cl minus. So these two, if you find out graphically, you will get a CH3CO minus and H plus. But you see these two ions, there we don't need them, isn't it? So you find out an electrolyte which contain both these ions, that is Na plus and Cl minus, that is sodium chloride. So lambda ion not of NaCl is equal to lambda ion not of H plus, Na plus lambda ion not of Cl minus. So from these two you will get the ions you require, and from this you can remove the ions you don't require. So you add equation 1, equation 2 and subtract equation 3. So what will you get? Lambda ion not of CH3 COONA plus lambda ion not of HCl minus lambda ion not of NaCl is equal to lambda ion not of CH3 lambda ion not of CH3 COO minus plus lambda ion not of Na plus lambda ion not of H plus lambda ion not of Cl minus of lambda ion not of NaCl. So minus of lambda ion not of Na minus lambda ion not of Cl minus. So this will cancel. That is equal to lambda ion not of CH3CO minus plus lambda ion not of H plus, that is equal to lambda ion not of CH3 COOH. So if you add lambda ion not of ethanoate ion, sodium ethanoate, and lambda ion not of HCl and subtract the lambda ion not of NaCl, you will get lambda ion not of ethanoic acid. These three you can find out graphically. For different concentrations you find out the molar conductivity of sodium ethanoate, HCl and NaCl. Plot them in graphs, extrapolate them and find out lambda ion naught. Add the lambda ion naught of CH3CONA and lambda ion naught of HCl. Then subtract lambda ion naught of NaCl. You will get the lambda ion naught of CH3COH. So in this way you can calculate the limiting molar conductivity of a weak electrolyte using Coleridge's law. So according to Coleridge's, we are going to find out the limiting molar conductivity of ethanoic acid. And lambda ion naught of ethanoic acid is equal to small lambda ion naught of ethanoate ion plus lambda ion naught of H plus. Now you will have to find out certain strong electrolyte which contain acetate ion and hydrogen ion. Now, if you take sodium acetate or sodium ethanoate, it is lambda ion naught of CH3COO Na is equal to lambda ion naught of CH3COO minus plus lambda ion naught of Na plus, and that of HCl you take, which will give H plus ion. So you will get lambda ion naught of H plus and lambda ion naught of Cl minus. And you want these two ions and you don't want these two. That means you will have to remove this. You take an electrolyte which contains these two ions, that is sodium chloride, which is a strong electrolyte. Then lambda m naught of sodium chloride also you have written. Now add the lambda m naught of CH3CON and HCl and subtract that of NaCl. You will get lambda m naught of ethanoic acid. So this is how we calculate the limiting molar conductivity of weak electrolytes using the limiting molar conductivities of strong electrolytes, which can be determined graphically. So that is from using one application of Coloraceous law. Another application is you can find out the degree of dissociation alpha, that is equal to lambda m at any concentration by lambda m naught is equal to alpha, the degree of dissociation. Alpha, the degree of dissociation, is equal to lambda m naught by at any concentration by lambda m naught. And what is equilibrium constant? Kc is equal to, last year you have studied, C alpha square by 1 minus alpha, that is equal to C into lambda m at any concentration by lambda m naught square divided by 1 minus lambda is lambda m at any concentration by lambda m naught, that is equal to C into lambda m square by lambda m naught square, lambda m at any concentration square by lambda m square, 1 minus, that is lambda m naught minus lambda m at any concentration by lambda m naught minus lambda m C by lambda m naught. This lambda m naught will go up. So what will you write? Lambda m at any concentration square by lambda m naught into lambda m naught into lambda m naught minus lambda m at any concentration. So this one will cancel. So it is equal to lambda m at any concentration by lambda m naught minus lambda m at any concentration. Okay, so that you can find out also the equilibrium constant.